Hello, welcome to another stream. In this one, we are going to talk about software architecture, and we are going to put a special touch on coupling and cohesion. So it's going to be unusual stream where we are not going to look into too much code, but more of like a presentation around the topic. And by the end of this video, you'll be able to design better software, and plus you will be able to detect things to improve or design flaws that you may pay attention to when designing your software. Now, as I said, we are gonna put a special touch on coupling and cohesion. And yeah, let's see how that's gonna go. So first off, I would like to start with what's the software architecture all about, or software design as a whole. So it's not a job for some clever person sitting in a cool office somewhere, usually. So it's more of like the choices that we all as a collective make every day when we are writing the code. So we can summarize it as like collection of organizing principles that we choose to apply on the code. That's how I see the software architecture. So essentially, it boils down to structuring. And when it comes to structuring, there are some guidelines, there are some principles that we have to follow, as we are going to see later on in the presentation. And when applied properly, the design tends to be good and or better, so that we can basically benefit from that. And then when it comes to benefits, um, why do we pay attention to the design and its structure or the architecture as a whole? Because of sustainability in general. So we want to be able to deliver sustainably. We want to establish testing. So we want to be able to test our software in a sustainable manner, and we want to also do maintenance of the software. And when you think about all those as a whole, in order to be able to deliver fast, in order to be able to establish the testing and do the maintenance properly, your software design has to be good. And in that sense, um, it will also allow us to work with the software better. So when there is a newcomer to the team, or when the software is, let's say, even us in the future, as the software evolves, it has to keep being simple enough to work with it, and easy to understand. So in essence, we are not computers. So if you give any design to a computer, it can compile the code, it can run the code. But to be able to maintain, to write the software, to scale the software, it has to be understandable from human perspective. And in that sense, we are not computers, so we pay attention to the software. Now, there are different architectures that you may be familiar with, and those are basically different principles that are mostly applied around the software design. Some of them are like MVP, MVC, ports and adapters, hexagonal architecture, and so on and so forth. And maybe you haven't heard of all of them, but you have definitely heard of clean architecture. And all those are basically talking about architecture as a whole, like software design. So by they're again applying some guidelines, some principles in a different way, so that the software becomes more sort of robust. Now, there are also books written on the topic. Clean architecture is one of them. Another one that is very popular is the design domain-driven design. Also, great book. Refactoring from Martin Fowler, and it has two editions. I think the second edition, this is from the first edition, this picture, but there is a second edition that is, oh no, this is the second edition I just saw. So yeah, this is also great book that talks also or touches about software design and testability and maintainability, of course. And also the programmatic programmer also has a bunch of chapters that are talking about the design. Now, all these books that were written, they all talk about the principles or the guidelines that we can leverage when it comes to designing our software. And now the thing is that all these books are also giving some examples to make a point. But the problem is that some people are taking that too much, not as like of a guideline or a principle, but more of like a law or like a rule, hard rule. And and then they are sort of sticking to it so hard that this is the only way. So these books are not actually showing the only way of doing things. They are more of like showing principles, as we are going to see just in a bit. And in that sense, what makes an architecture good? Maybe we might ask a question. So what makes it clean or pragmatic? Now, every project, like we have to internalize literally that every project is different and unique. Just like I heard this somewhere, just like any house or any object, like physical object out there, any building is a unique and it serves different purpose. I mean, doesn't serve different purpose, but it is sort of designed in a different way. And in that sense, it has unique needs and doesn't, and in that sense, it means that probably it is going to be different than something else. And when it comes to guidelines and principles, we just have to respect so that the things are not breaking apart. But the actual implementation can be a little bit different, or it might vary depending on the needs of the current project, what we are currently doing. So what I'm trying to point out is that we shouldn't really follow blindly anything we see on internet or read online or read in books, but rather do the practice and figure out what are these guidelines, what are the principles that we have to keep in mind, and then when we apply them, it's going to work in any sort of architecture or design. And we will see what are those just in a bit. So the first thing I want to talk about here is the abstractions. So any language out there, any software is basically exposing or letting us to work with abstractions. Depending on the language, it might be like these abstractions are low, like can be very low level of abstractions, and they can also go higher in hierarchy. So when we are talking about low level of abstractions, so we can first think about primitives. So every language has primitives, and we can even boil down to, like, I don't know, references to some memory allocations and so on and so forth. But most of the time in languages, we work with primitives. And these primitives are types like string, integer, boolean, and so on and so forth. Now, a little higher level of abstraction would be when we combine these primitives. So we are defining our own types where we include some of these primitives, and then we are talking about domain data or models or types, depending on what you prefer to call them. Now, they might appear in a form of a, like, let's say, contract or a user or an account. So it has some properties which are in a form of an abstraction or another domain type that also is constructed from abstractions. And these types are slightly higher level of abstraction compared to the primitives. Then on top of that, we got functions. And now these functions, depending on the language again, they mostly live inside a class, as we're going to look into just in a bit. But yeah, we have functions, and these functions are operating on these domain data or models or primitives. So these functions are higher level, just a little bit higher, and they operate over this data. And this is really crucial, as we're going to see, so pay attention. Then, as I said, these functions, most of the time, or depending on the language, may live in classes. And then these classes can go in packages, in modules, in services, in whatever, like depending on like how we are going to grow. Is it backend, is it mobile, is it whatever? And also language-wise, it might depend. So we've got those, and it can go up, but the point here is that we need to make clear to distinguish this clearly, these two worlds. So there should be clear distinction between the domain data or the primitives and the functions and everything above. And we are going to take a look why. So these functions, as I said, they mostly operate on data. So they would take like either primitives or domain types, and they operate on them. They get them in, they return them, they do something with them. And these functions, most of the time, as I said, live in classes. But on the flip side, also depending on the language, the domain data or the models or those types are also represented with classes. And that is maybe the biggest problem with the languages, because especially when you are a beginner, when you start with programming, this is pretty much confusing. So what the class should do. Now, languages like Kotlin, for example, do have data class, which makes that distinction a bit better. So that we have, okay, data class means data, means type that holds some sort of domain model or domain type that holds data. And then we have regular classes that are sort of operating over that data. Since Java, I think 2019 or 21, I don't know, we also have records, or maybe it was Java 17, doesn't matter. We have records. Ruby also has records. Now, this is better distinction, of course. And what's the point here is that these that are below this line, they are data, or with other words, they are details, essentially. So like they represent some sort of piece of function, piece of data that gets together, and those are details. These other things on top, they are representing operations that can operate over that data. Or maybe you can find them as like domain services at some places, depends. So in essence, there is this distinction between the domain services and the data. And that's where the cohesion and the coupling are coming into the game. So when we talk about cohesion and coupling, the coupling between these two, between the domain services or operations and the data, the better. Now, when we are talking about cohesion essentially is intentionally coupled abstractions. I'll explain just in a bit. What we need to remember here is that we could not physically decouple everything. So there must be some form of coupling between these two worlds. We couldn't bring it to zero, to none. But we have to understand that, okay, we put together things that want to stay together, that want to live together, and that belong to the same or similar abstraction level. So if you're thinking about that, we put, for example, in a data class, we put some properties, let's say name, user, or like name, last name, age, whatever. They represent a user. So they want to live, they stick together. But the operations around that user probably will be in completely different world, in another class that does operations over that user. And in a sense, as I said, because the things want to stand together, let's actually take a look into maybe a concrete example. Let's imagine a class. So a class may have few functions. Here I have 3 functions. So that class, we can say that it is a cohesive unit because it adheres, let's say, to the single responsibility principle, even interface segregation principle, because it collects functions that are sort of working over specific operations that are working over a specific thing. As the code evolves, we may detect that, okay, now this function 3 does no longer belong to that first class, so we can extract it into another one that's gonna be much better separated in terms of, let's say, single responsibility principle. It may operate on certain abstraction level, like these two may operate on certain abstraction level, and then at some point we may need to combine the functionalities between these two classes. So when it comes to combining these, we can introduce, let's say, another type that will be talking to these two. Now, when you think about the relationship between these two, we have a client-service relationship. With other words, the class 4 is injecting class 1 and class 2. so that it can talk to them. So if you think about this, what's being injected where? Class 1 and 2 are being injected in class 4. And class 4 then can utilize the services of class 1 and class 2, or the functions that it provides. So it can operate on different data. Now we may realize that, okay, at some other point we may have another class that talks to yet another class. So this, like, especially if you're practicing test-driven development, there is this thing called evolutionary design. So this design evolves as a consequence of what the tests need. So how the tests are evolving, how the software evolves based on the of the demands, these classes are sort of arising. And at some point, maybe we are going to have yet another one that needs the services of all of these. So this is, like, I'm trying to fit everything now in the slide, but this pretty much represents an object graph. So when we are talking about an object graph, in class 6, if we pay attention here, class 4 and 5 are being injected, and into those, class 1 and class 2 are being injected, and class 3 respectively. So the construction, if you pay attention here, the construction shouldn't depend on details. And that's the first principle that we have to understand from this presentation. Details being these data classes or records or whatever you call them, or primitives, when the classes are not depending on them, we are actually, now of course there could be a situation, we are going to take a look just in a bit, but there could be a situation, but like we shouldn't mix them. In essence, the less we depend on details, the more, the better the structure, or the easier to work with. So we are going to witness that. Okay, and now when we also take a look in this picture, we can sort of think of layers. So the software is split in different layers, and each layer operates in different abstraction level. So class that operates on that particular abstraction level can belong on a specific layer. And when we combine all of this together, we can talk about, okay, this might be our domain. So our domain has, like, or the way at least I am picturing that in my head, I am seeing it as this square here, and then that domain has lower levels of abstraction and higher levels of abstraction. Give me a second, I'm sorry about this. Okay. So yeah, we have layers that deal with lower level of abstraction, and I am projecting that or thinking about that in my head. I'm imagining it this way. So those lower levels of abstraction actually are more towards the external, like how the system communicates with the external world or external systems like HTTP or database or disk or so on and so forth. On the flip side, we have higher or layers that deal with higher level of abstractions. And they are more towards like the delivery mechanism of the entire system, which might be in a mobile application, the actual screen. So the screen, for example, can just get some data and then pass it through the whole software or the whole domain. So we are gonna look into how the data flows just in a bit. Now, back to our object graph. A loosely coupled system is when the system, like when we construct this without relying on data. So we have a rock solid construction, and wiring is not depending on the data. So like we can wire these at any point of time, and it's a rock solid construction, and then the data can flow throughout. So for example, a data might come in, and the data is dynamic, meaning that it can just flow throughout the system in and out. So this box being our system, the data might come in, and it will just travel throughout these layers. And for example, we can think of a screen that contains, let's say, some sort of form, and that this form collects some data, like literally strings, and then these are maybe strings are being passed through, and they are sort of wrapped into some form of data class. So we can pass them throughout the system. They may travel the layers, and while traveling the layers, the data might change as it passes through. It may get enhanced. So maybe the system can sort of persist some stuff. Let's imagine, I don't know, authorization token. And then this authorization token can be included, let's say, in this data while flowing throughout our system. And then at some point, it will reach a boundary. And this boundary is an integration point. This integration point is a point where our system integrates with another system, external, being, let's say, HTTP or database or disk, whatever. It's outside of our system. So it leaves our system, and then we, like in a response, we might get, as I said, a response, like another form of data. Like this data comes in. Now, when this data comes in, it hits us at a lower level of the things, and then we have to think about some transformation. So, for example, the entities that may came from a database or from a HTTP, we are going to maybe transform them, or it's a good practice to transform them to domain types, domain data. Or, for example, low-level details like, I don't know, IO exception, even the exceptions are not an exception in this transformation. So those exceptions also, if you prefer to work with them, you should introduce domain exceptions that are not you are not coupling your system with something that is like too generic. So it will represent your domain properly. And as the transformation happens, the data also may, like the data is traveling upwards, but also some transformations, as I said, are happening. And here I really want to, point out something that I'm seeing in variety of projects related to Android development. When I'm seeing layers or sort of level of indirection that are acting as a middleman in a form of like usually they are called some like a use case, but here is an example of what I'm thinking. So here I have a class that is like a use case injects repository. So this is the point here. It would have only one function that is usually called execute, or it's going to be an operator function even. And what happens here, it returns list, same what the repository returns, and it just forwards the call. Now, maybe like it would be better if there is a reason, if this type actually does something in a form of maybe data transformation. It could be, or it could be something else that the system needs. So one example would be, for example, this one would return domain model, right? And then when it returns domain model, then we have to introduce some sort of logic here that will try to get the data, convert it somehow into a domain model and return it. Or in terms of like, if there is an exception, it would convert that into an exception and then return back that domain type. So now we have a reason for this type to exist. Back to our object graph. As I said, the data is traveling upwards now. Again, as we saw, it can change, and it should change from whatever primitives are coming in, or lower level details, or data that is known for the external system into data that we are mapping it into our own, and then we are transforming throughout towards the delivery, and then finally we are going to show it to the user, or if we are thinking about API, we are going to send it as a JSON, depending on the project. So as we saw, the data can freely flow throughout the system, but the system stays rock solid. Once we construct it, it doesn't change much. So the construction of the graph is not depending on details. So we can wire it manually, we can wire it with DI. It really doesn't matter how we are going to do that wiring. Once we wire it, it's rock solid. So there are these, probably you are aware of, there were some, at some point, some tooling like assisted inject. So that's clearly like an indicator that there is a flaw in the design that you can improve, of course. So as we saw, there are two things that we have to pay attention: respecting, and then also aligning to these principles and guidelines. When it comes to respecting, as like if we are thinking of our object graph as layers, we don't want to do too much of a jump between the layers. So for example, one layer should not jump over another to make a call. And this is like, because I have just as much space in the slide, I'm just having 3 layers, but like this is not exactly like jumping one layer. It can happen, but jumping too much of, like, I don't know, 2-3 layers, then it depends on the software that you're writing, then it might become a problem. And I'm actually having this slide only because I want to show an example of what I saw in my experience in software systems. So this is one example of a recycler adapter. So when we take a look, this is just a recycler adapter, and recycler adapter really belongs to, it's a very specific UI component, right? And what happens is that here it injects use case, and even worse, DAO. So the use case, it's like, this is the UI. Like if you're thinking about, I'm not sure if you can see me, but like the adapter being part of the UI is so much higher level of abstraction compared to the use case or even the domain, the DAO. The DAO is much lower. And now injecting them, we are making, like, we are coupling the UI with such a low level of a detail. This makes it so hard to maintain, to work with the system, to do anything when we are doing this. And I saw this in one of my previous projects back in the days. This is clearly a problem. What mostly we would like to do in this case, it could be, let's say, like we can expose a callback of, because this is a UI element, this adapter, like we have some items there and we can do operations on these items, but when we perform an operation, they would come back as like in a form of a callback, and then whoever owns or operates with this adapter, let's say a fragment or activity or whatever, some UI controller, it will get that callback and it will then proceed down the, like that data, it will proceed, or that action, down to the levels of the architecture. And again, back to the that would be about the respecting. In terms of aligning, let's take a look into yet another example. So here we have a view model, and then this view model depends on a contract, which as we saw at the very beginning of this presentation, was a detail. So to construct this view model, we need a contract, and this contract is a, let's say, data class or a record, and that actually is a problem. And then the second dependency is like some class that does operations, like analytics, like tracking. So we are mixing both of them together to construct the view model, and that is the issue here. So what we can do better, we can actually, instead of getting this contract, we want to avoid abstractions depending on details. And what we could do to improve this, we can actually get this load data to take in the contract, or whatever function that we may have inside this view model that needs that contract. We can make that function take that as data and then do what it needs with that data. And in that sense, we are actually decoupling the view model creation of that data, and we are losing the coupling. So we are going back to actually having that stable construction and the wiring. And now the contract can be like, it comes from somewhere. We can create this view model without having the need of the contract, and we can say, okay, here is the contract, do something with it. And on the flip side, as I mentioned before, there could be a case when we are constructing details like this UI model. And I've seen also examples when it would inject something that does operations, like a use case. That's also like, this is the vice versa. This is also an issue because it's a UI model. It should depend only on another data. It should not depend on operations, right? And in that sense, just because you can, doesn't mean you should. So like the languages are not that much restrictive or that much, pointing to us to tell us, okay, this is an issue. So this is something that we have to listen to. We have to observe these things and then think about them, what actually we are doing. So because the language couldn't literally like restrict us of doing bad things, doesn't mean that we should do them. With other words, just listen to the architecture, listen to the feedback you get from it. Is it hard to work with? Is it hard to test it? Is it hard to maintain it or just refactor? Well-structured code enables testing and refactoring. So when you're having issue to test or refactor some code, means that you're having some sort of design flaw, and means that you need to pay attention to design and you have to improve it. Now, if you want more of this, if you want deeper learning, if you want maybe coaching or mentorship or guidance, how you can actually do better in these areas, if you want to learn by hands-on practicing and getting active feedback, then I'm actually adding 2 links below in the video, and you can come talk to me, and then we'll see how we can help you further. So those links are going to lead you to the Android devs community, which is a community of a lot of people, over 1.1K, close to 1.2K. And you can find the link here as well. And basically that would be it. I would like to thank you for the time and the attention. And now if there are any questions, I would like to hear them. Now we got some people in the call, we got some people on YouTube. So yeah, if there are any questions, please let me know. Go ahead, Anthony.
All right. Thank you very much, Jeff, for
You're welcome.
this session. I've actually been looking forward to this, and this is really interesting for me. It's something that personally I would love to pay more attention to going forward. And I just wanted to thank you for this session. Yeah.
All right, thank you so much. And also I would like to apologize for like insanely like unbearable temperature that I'm having here, and maybe it's noticeable that I'm all sweat. But yeah, maybe it made me a little bit underperform, but I hope the presentation was okay. Yeah, thank you for the recommendation about the community in the YouTube chat, and thanks for the kind words. Okay. If there is no questions, I would like to thank everyone for attending, and of course you can go back to this video on YouTube at any point of time. And as I said, you are very welcome to join us inside the community if you want to learn more or like get more sort of guidance, mentorship, coaching, anything you want. That would be it. Thank you so much, and I'll catch you next week.